Hello, I am JeongEun Park from Online Lab. My term project is about robust human-in-the-loop task and motion planning. To begin with, let me introduce about human-in-the-loop. It is similar to active learning. We are given a bunch of unlabeled dataset, system asks uncertain data, unlabeled data to human, and train based on this data. So why do we need robustness in active learning? Like this example say, robot has to avoid tree and get to the flag. Robot will become ambiguous whether to go past 1 or past 2. However, expert will be uncertain too, resulting in giving a noisy dataset. This project combines this robust active learning with task and motion planning. Like in this figure, to achieve high-level goal, it divides each task with low-level goal and achieves it. Our problem formulation is non-prehensile manipulation, where the manipulator can only push the obstacles and get to this green one. This is non-prehensile because pushing one can affect other obstacles' position. I use it 5 LED with your 5. For toy task, I use it for obstacles with fixed initial location, and for the main task, I use it 5 obstacles with random initial location. To solve this task, I first divided high-level global planner and low-level local planner. With n obstacles, I made global planner as n+3 label classification task. Each option is as seen in this down here, and I will come back to this later. As global planner, I trained a mixture logic network. It is a modified version for mixture density network for classification task, and it can estimate uncertainties from output of mixtures. For human-in-the-loop learning, I first set the threshold, and if the uncertainty is bigger than threshold, human annotates, and if it's not, robot just acts. By mixture of logic network, uncertainty can be obtained by its output. Mixture logic network is consists of mixture of experts each giving predicted distribution and noise. Epistemic uncertainty become how different each expert's predicted distribution is, and average of each expert's estimated noise become aleatoric uncertainty. This model is robust because for noisy dataset, mixture of experts makes better representation. I use a total uncertainty as sum of aleatoric uncertainty and epistemic uncertainty. Possible cases for high uncertainty is like in this figure. I made an example of 4, first one is about when the robot is at initial state of training, and other will be out of distribution or maybe hard problems, or maybe for the mislabeled dataset uncertainty will go high. To sum up, given an environment state, the robot decides whether it is certain or not, and if the robot is certain, it just do its action. And if not, they request label to experts, and given experts label data sets, they store them in memory and train the model. For local planner, I use heuristics. For pushing these obstacles, if the obstacle is right on the side, it just push it on the right, and others is just what you see. It will move a robot to align axis with the goal, or move robot to the goal, or maybe if something goes wrong, then move robot backward. To confirm my formulation is right, I made heuristic global planner and tested it. And this is the algorithm. And first they align robot with x-axis with goal, and then get this blue area where the given threshold, they just find the obstacles in this blue area, and then select first one from the blue area, and then just push it, and then it goes in the loop. And when there is no obstacles in this blue area, they align axis with goal again and get the blue area again. And if there is obstacles, they go back in the loop. Or if there is no obstacles, they just move to the goal. So I tested it with Global Planner and it works pretty well. So I thought that this will be this classification task will be right. To test robustness for toy example, I annotated 3 suboptimal and 2 optimal during training. And even with these situations, the model tends to work pretty well. And with 5 obstacles with random initialization, I trained it model with fixed epoch for each step. The model tends to be unstable, but it seems like it's working. What I found was that even I made a lot of mistakes when labeling, and robots make mistakes too. And what was fun was that if the robot makes mistake, the uncertainty becomes very high, and it asks experts what to do. And this is what robots do well. I try picked, yeah. And to fix the unstable learning problem, I just train model with until accuracy becomes 90% for every step. The work clock time increased, but it becomes more sample efficient since it finished only in 17 episodes. The last one will end up with 43 episodes, so it becomes very fast. The model becomes stabilized, but the problem was that the model became too overconfident. So this is the video, and even robot and human annotator still makes mistakes, but it learned pretty well with only 17 episodes. So the limitation in future work will be that I didn't use any visual inputs. I just used it just obstacle position and goal position and robot position. So using visual input will be more fun, and there might be another way to use heuristic local planner. And the main problem was that it's not still working perfect, and there will be other solutions than just training until the accuracy becomes high. There will be other solutions, and the problem was that human has to annotate around first 20 minutes, and it was very hard for time, so I need to fix that too. And thank you for listening.